Hi, how are you? Hope you're all doing fine. Today we're going to discuss about a three-phase induction motor working principle. I'll straight come to the point. What is a three-phase induction motor? Three-phase induction motor is undoubtedly a very good motor, a workhorse in all the industrial applications. Recently I have made a visit to a cement mill, cement industry. There, the cement mills and raw mills are being controlled, are being operated with the help of induction motor, three-phase induction motor. A crusher, I have seen a crusher. The crusher is the one which crushes the limestone, which is of a big size of limestone is crushed with the help of a crusher. The crushers are being operated with the induction motors, and that too specifically about three-phase induction motors. And I personally like this three-phase induction motor as because it is a induction motor. Okay, so what is the significance of the term induction? Whenever I take any topic, it's my usual practice to explain about the title. What is induction motor? What makes it to have this title? Very simple, a well-known answer that can be given is like because there is a principle of electromagnetic induction in this motor, we do have this name. Okay, what is electromagnetic induction? Electromagnetic induction is nothing but a process in which the energy is transferred from one circuit to another circuit through the process of electromagnetic induction, through the process of flux transferring. Okay, so how does it happen actually? You can see a single phase transformer. Single phase transformer has primary winding and secondary winding, and in between these primary and secondary windings you find an air gap, or you can connect to a core shell type or core type structure you can keep, and you can have both primary winding and as well as secondary winding. And between these primary and secondary, you need to you are transferring the voltage from one level to another level, maybe from high to the lower level, or from lower to the higher level. Based on this you can say it's step up or step down. So what exactly happens there? The flux that is induced in the primary winding will link to the secondary coil, because the flux which is changing in nature is linked with the secondary coil. Secondary coil also, it has its own EMF induced as per the Faraday's second law. What is Faraday's second law? It's called about the method in which the Faraday's second law is used is statically induced EMF. So anyways, here the EMF is induced in the secondary winding in the aspect of in a process called electromagnetic induction. Similarly, induction motor also has two different windings here. The first one is a stator winding, the second one is a rotor winding. Stator winding to rotor winding, the energy, the flux is is common for both the windings. So what happens here is the energy that induces in the rotor winding, the current that is induced in the rotor winding is not through the process of conduction, but it is through the process of induction. I'll come to the quickly come to the point here. Whenever, if you find any motor, and if it is if you see the working principle, the only working principle that exists is you need to have a current carrying conductor placed in the presence of the magnetic field, and thereby the flux which is there will act on the conductor in such a way that the conductor would rotate, or the flux will act on the conductor, and thereby a force is produced, that is F is equals to BIL sin theta, by which the conductor rotates. This is how any motor works. But now current carrying conductor is required, not a normal conductor. Hope you're getting the point. The current carrying conductor is required. So what is meant by this? If you take a DC motor, we'll not call it as a induction motor, but rather we can call it as a conduction motor. You know why? Because DC motor, the rotor has the conductor, conductors which are placed on the rotor winding gets the current through the process of conduction. What is that? The conductor the current carrying conductor or the conductor, whatever that you find in the DC motor rotor winding, that conductor gets the current from the battery and then into a brush and then into the commutator segments, and then it flows into the armature conductor. And this is how the current is given to the rotor winding through a physical wire connection. Hope you're understanding me. The current is given to the rotor winding through a physical connection. That's why I would call it as a conduction motor. But in the case of induction motor, you don't have any physical connection between the supply or between the rotor winding and any other auxiliary things. Rotor winding is a standalone winding. It is not connected to anyone. If you take squirrel cage, suppose if you take slip ring, then it's a different story. We'll take that windings out and then connect some rheostat to that so that you can vary the resistance by which you can vary the torque. That's a different story. But in general, a squirrel cage induction motor, if I take, the rotor winding is a standalone winding. The rotor conductor cannot and doesn't have any physical connection from any source. So how does the rotor winding or rotor conductor gets the supply current or current through the rotor conductor? How does the induction motor rotor conductor gets the current? It gets the current through the process of induction. That's how this motor is called, the induction motor, in which the rotor conductor gets the current through the process of induction without having any physical connection with any source from the outside. No auxiliary source, no external source is connected to the rotor winding, but still rotor winding gets the current. It has its own current. It will have its own flux later on. So that's the beauty of this particular induction motor, which makes it which makes the motor a little significant or a different motor compared to any other motor. So now let me take up the working principle of it. So if I have to take the working principle, then definitely I should take a little construction of it. So I will call this as my the stator, and then I'll take the inner sides of this stator winding, the stator. Fine, this is a core. Fine, outer portion is called yoke, which is very strong cast iron made. Now there will be some windings in the stator. Okay, so usually if you take any motor, you will have stator and the rotor. So in the stator, you'll have stator windings. Rotor also has rotor windings. Okay, but the difference between the stator winding and the rotor winding is, if I take squirrel cage induction motor, the difference is like the rotor windings are made with bar conductors, big conductors, maybe a size of this pen. So, but in the case of stator winding, it's a normal copper wire, a sleek, slim conductors are used to have that. But whatever, stator winding is a three-phase winding. In fact, three-phase distributed winding. So what is it? Three-phase distributed winding. But rotor windings are not so. These are general general windings which are made with bar conductors. Now let me take up the stator winding on the stator and then the rotor winding on the rotor. So let's take I have a conductor here which I call as A. So as I am specifying about the distributed winding, I need to take a distribution of three-phase over the 360 degrees. Now all the conductors are to be spread or distributed among three different phases. So I'll take my first coil with a coil side A here, and then at exactly 180 degrees shift, I'll take another coil side. So I name it as A dash. Okay, and then I'll take exactly after if I take this as my center point, after that exactly after 120 degrees I'll take another phase, the conductors which are under phase B, with a phase difference of 120 degrees. Okay, so if I take one coil, one coil side on this side, which is B, I'll take another coil side on the exactly opposite side of it, B dash. This is how it is, B dash. So now I have finished two different, two coils on the stator winding. One is under phase A with a angle of 0 degrees reference angle, and then the phase B with a phase shift of 120 degrees. Now let me take another winding which is about 240 degrees. From here to here again, if I take 120, so from 0 if I take, it's going to be 240. So I'll take another winding which is here called C. Another coil side, and coil will have a coil side, so coil side C dash, C and C dash. Okay, hope you are understanding me now. So there can be many conductors under phase A, there can be many conductors under phase B and under phase C, whatever it is. Every conductor, whatever that you find this side, the counterpart should be there on the opposite side. So if I have 3 here, there will be 3 here, A dash or A1 dash, A dash, A1 dash, A2 dash, something like that. So whatever that you find in this axis is called phase A windings. This is how a simple understanding of distributed winding. Distributed winding means these are the windings which are distributed over 360 degrees with respect to its phase angle. Okay, so this is how I can take about 3-phase distributed winding. And now let me point out, let me put a description on let me explain, let me put a description about the rotor winding. Yes, rotor winding is supposed to be here. Rotor winding is supposed to be here in the middle. So I'll take the rotor winding here. Fine. So I'm not so good in this drawing, but still I'll try my best to make it. Okay, this is my rotor. Okay, and this is the rotor core, in fact, in which I have my bar conductors, big conductors. Okay, right. This is not a 3-phase or a single phase winding, it's a general simple winding, and all these are short circuited inside. They are connected. If the circuit of rotor winding is closed, if it is a squirrel cage, so it's a closed circuit, and here you have shaft. Okay, now you see this is about a simple construction of it. If it is a squirrel cage rotor, okay, if it is a slip ring rotor, then the leads are taken out, connected to the slip rings, and then you can have a 3-phase rheostat connected, by which you can change the resistance. But here in the case of slip ring squirrel cage induction motor, you will not find the resistance, you cannot change the resistance. You will find the resistance of the rotor winding always constant and consistent throughout the operation, from no load to full load. That's fine, that's okay. Now let me go and explain the working principle a little more deeper way. So if I give a 3-phase supply, okay, 3-phase supply. So what is this supply? 3-phase supply. So VA at an angle 0, VB at an angle 120, and VC at an angle 240. Okay, then the current flows, what is that? IA, IB, IC. The current flows through the windings. That also has a phase difference of 0, 120. I can indicate that too. Now what will happen? There is a very good important thing, very important thing that I need to mention here. Whenever a 3-phase supply voltage is given to 3-phase distributed winding, then what will happen is there will be a 3-phase flux produced, phi A, phi B, and then phi C. Okay, whenever a three-phase supply is given to three-phase distributed winding, then what will happen? Three different flux components are produced which are about 120 degrees apart from each other. So then what will happen? The resultant flux is a combination or is a vector of three different flux components, and this flux is a rotating magnetic flux which rotates at a speed of 120 f by p, where f is the number of f is the frequency and p is the number of poles on the stator winding. That's fine. Okay, so what is this? Whenever a three-phase voltage balance, in fact a three-phase balanced voltage is given to three-phase distributed winding, then that will produce three different phase fluxes, and the resultant flux of these three flux components is a rotating magnetic flux. And that's how the flux what is produced here is a rotating magnetic flux, and even this field is called rotating magnetic field, RMF, not EMF, RMF. Okay, so rotating magnetic field. Then now the flux whatever is produced here, or the field which is produced by the stator winding, is a rotating rotating field. By its nature, I mean to say by its virtue, it's a rotating flux. You're not rotating the winding. Make this point clear. You're not rotating anything on the stator. You're not rotating the conductors. The conductors are kept safely on a stationary body which is stator, but still the flux which is produced by this three-phase distributed winding, because of three-phase balanced supply, is a rotating magnetic flux. So the field which is produced in the air gap between stator and rotor is a rotating magnetic field. That's why it's called a short note of it is RMF. Hope you got until this point, right? Now what will happen? See, this rotating magnetic field is rotating at a very high speed called synchronous speed. It will be revolving there in the air gap. But what you got in the middle of this, in the midst of this flux which is rotating at that speed, you have a rotor which is static, which is stationary, which is not moving. Then what happens is that this flux which is rotating would cut the rotor windings. When this flux cuts the rotor winding, then what will happen is rotor winding will induce its own EMF. That is called E2. That is called E2. And because the windings are closed, you will have its own flux I2. Okay, now I'll stop here. So what I said in the beginning, DC motor also has a current carrying conductor. In fact, any motor, you should have a rotor, and the rotor conductor should have some current. Okay, see, in the DC motor you have the current through the rotor conductor through a physical connection. You are having a battery connected to the brush. Brush is placed on the commutator segment, and commutator segments are with end rings. They are connected to the rotor windings inside. So you have a conduction that is happening to give current into the rotor windings there in the case of DC motor. But here, how does this rotor is inducing current in it? There is no physical connection, no external wire is connected. It is only through the process of induction. What happened just now I explained, right? What happened? The rotating flux would cut the EMF. When the rotating flux would cut the EMF, then thereby, when rotating flux would cut the conductor, thereby it has EMF induced in it. Okay, and once the EMF is induced, because the rotor winding is closed, you have a current flowing in that. And then what happens is, as per the DC motor principle, whenever a current carrying conductor is placed in the presence of magnetic field, see, now the conductor is having a current, right? So because the conductor is having some current and it is in the midst of the magnetic field, then what will happen? A force F is equals to BIL sine theta is exerted on the conductor and thereby it moves. This is a simple, I can link the DC motor principle here and I can wind it off. But still, if I have to make it a little more elaborative discussion, I'll just add two more statements now. Something like, because there is a current flowing in these windings, okay, because there is a current flowing in these windings, it has its own flux. It has its own flux, maybe phi 2, okay. So this flux will have an interaction with phi r. These two will get interacted. As like the DC motor, the rotor flux and the stator flux will have an interaction. Based on the interaction or because of the interaction, the flux lines will get bent, and as the flux lines have got a elasticity property, they don't get bent for a longer time. It tries to come back to the straight line position. So in regaining its position back as a straight line, it tries to pull the rotor down in the same direction as the RMF is moving. Okay, so now the rotor is rotating with a speed called NR. Let's say I'll take the shaft out, and because of that the rotor is now rotating. Very simple, right? So the most important point, induction, the current is induced in the rotor through the process of induction but not through the process of conduction. There is no physical connection that is made. This is a very simple discussion that you can have. And now, how many speeds are there? There are two different speeds. One is the speed of the stator field, the other is the speed of the rotor winding. So here, whenever we make some discussion, even in the future lectures also, if I say stator speed, it's a synchronous speed. So if I say stator speed, it is not the stator which is rotating. In fact, the flux of the stator which is seen as rotating. So it is a stator flux speed. So ns is the speed of the stator flux, and nr is the speed of rotor itself. Okay, complete rotor at which the rotor is rotating. And now if I take any nameplate details, I'll find the speed notification there. I'll find the speed notification as about 3000 rpm, or you would find maybe 2000 rpm. So what is that speed? Is it ns or nr? Undoubtedly it is NR, because you will always be given the speed at which the motor is running. So this is the speed at which the motor is running, entire mechanical setup is running. But there is a the speed which is, there is one more speed which is ns, which is the speed of the stator winding that you have with the equation 120 F by P. Okay, this is how you'll have it, right? And now coming to the P is actually not a magnetic pole that you find there. It's a electromagnet, the artificial magnets. To say the set of conductors will act as a magnet. So based on that set of conductors which are acting as one pole, then you will have to decide about how many poles are being kept there. Okay, you'll not have more than 6. In certain times you can go up to 6, but usually number of poles will be P. It doesn't mean that number of poles will be 4. It doesn't mean that there are only 4 conductors. Okay, no, it's actually a set of conductors which act as one pole. That is considered to be north pole. Maybe 30 conductors may be acting as one pole, or 150, 300 conductors may be acting as one pole. Likewise, you may have a 4-pole machine, or a 2-pole machine, or a or a 6-pole machine. Definitely you'll have even number for the number of poles, and thereby this is how I can tell you about certain things. And now in the next discussion, I'll just make it on RMF. Okay, have a nice time. Thank you.